Okay, so what I've done here to show you what we're doing is I left in the code from yesterday. Remember we did 5/9, the moving average, minus 32 plus 273 to convert it to
Kelvin.
And then we then did 100 times
that?
The last minus the first divided by the first to get the percent.
Alright.
Okay. Here, so I left that in just to remind you what we did. Here, I'm doing the same thing. I'm looking at our data, our temperature data, grouped by county. And now I'm doing using a function called fit. And what fit does is it says take 1x. So I'm fitting it. What is the equation that is a plus bx? What kind of equation is that?
A plus bx, so there's going to be a line.
That's a line, right?
So that's probably our best fit line.
So I'm fitting our data to a line. I'm also multiplying, I'm taking the coefficient, the x coefficient of the line, and I'm multiplying it by 100. And the reason I'm multiplying it by 100 is that, what is the coefficient, the x coefficient? If you have a line that's y equals ax plus b, what is that b?
That's the y-intercept. Like, what do you mean?
Oh, sorry, b, I meant to ask a. Y equals ax plus b. Yeah, sorry, I asked the wrong question. What is a? What is that called? Ax plus b.
A is the slope.
A is the slope. And the slope represents what the change in temperature is each year. So we were looking over 100 years, and so the 100 times the slope is a representation of.
So it makes it, I guess, not as small.
Yeah, but what is 100 times the slope? If the slope is the change in temperature each year, 100 times the slope
it's
is
the change in temperature over 100 years.
100 years, yeah. And then I just executed all of that code, and I got this graph. Okay.
Alright, so it's similar to our previous graphs, but not quite the same.
It does look actually a little different up in like Maine. Before that was pretty dark red, but now it's sort of just kind of medium red.
Okay. So I want to ask you, why might this be the same? So what we're doing here is we're looking at all the 100 years of data and finding a best fit line. However Mathematica does that. I'm not going to get into the details of that. But it finds a line, and we saw those lines, and they looked okay.
Yep.
And then previously we looked at the first 10 years and the last 10 years and the change over that. So why do you think these might be similar graphs, just conceptually?
Well, that's kind of how you find the slope. You can, I mean, maybe not for the best fit line, but to find a best fit line, you could take the last data point minus the first data point.
Okay. Yeah, and we didn't quite do the last minus the first. We did the 10-year average, the last 10 years and the first 10 years.
Alright.
Okay, so can you explain why you think these might be relatively similar?
Well, if you're looking at, if you're looking at the old data, we have data from 1919 and the data from today, I guess you can create a line for that, and that'll probably look similar to the data from today, so those lines might be similar.
Okay, and which one do you think is going to be better if you wanted to approximate it with a line? Using this best fit line, or using just the first 10 years and the last 10 years?
The best fit line is going to be better.
Okay, why?
Because the 10-year one doesn't, it only gets it at the start and the end of the best fit line. Gets it better for all of them, and maybe it's not as good for the first and the last.
So the best fit line takes into account all the data, rather than just the first and the last. But you can see, we get a graph that looks somewhat similar, and we could now use this best fit line to make a prediction if we wanted to, and then we could see how that prediction would go. So my next question is, how do you think we could improve the prediction, or possibly improve? I have to be careful here because this is a very hard topic. What do you think we could do that might be a little better?
Well, the temperature increase isn't linear. Like it's not always linear for the counties. Like over here we saw it decreased first. So maybe we may not want to use a line. We could use like a parabola.
Okay, interesting.
Or maybe an exponential.
Yeah. An exponential or a parabola. Now you studied a little bit of calculus this year. What can you tell me about the relationship between exponential e to the x and a polynomial?
The exponentials grow much, much faster.
Okay.
So,
Can polynomials be used to approximate e to the x?
yes.
How?
For, like, the formula for them?
No, but how? What's that topic in
That's
calculus?
Taylor series.
Taylor series. So I'm going to simplify using approximating by an exponential, which is a little more difficult, by just simply using a parabola. Okay?
All right.
And we'll take a look at that parabola, and we'll see if we get a different look at the data. Okay?
All right.